Hello and welcome to our session at the NCTM virtual conference, session number 1177, Shapes and Tiles, Engaging Creativity and Neurodiversity in the Math Classroom. Hi, I'm Marina Basu. I am a researcher at Arizona State University, and my research interests include creativity in elementary math teacher education and non-Western approaches to creativity. Before this, I was a mathematics teacher, teacher educator, and curriculum developer in India and in the US for a number of years. Even while developing the curriculum and teaching in the classroom, I was interested in looking at cross cultural contributions to mathematics. And that interest is what drives me to the presentation today.
Hi, my name is Anani Vasquez. My past experience is in elementary education as a dual language teacher, gifted coordinator, and special education resource teacher. I have also been a teacher coach, mentor in a professional development school, and an ASU course instructor for elementary mathematics and math methods for elementary teachers. I've had training and practice in cognitively guided instruction and other constructivist methods for teaching math. Currently, I'm a researcher of neurodiversity and creativity in education and research methods at Arizona State University. This presentation will begin with some of geometry's big ideas, followed by examples and information about tessellations. The last part of the presentation will be a discussion on rich tasks, creativity, diversity, and equity. Finally, we will end with an invitation for further discussion. The big ideas in geometry that we will be touching on in this presentation are objects and the space they occupy can transform. Objects, relationships between objects, and the space they occupy can be quantified. Properties of objects can be classified. While exploring these ideas, we might ask ourselves, what changes and what doesn't? How can shapes and spaces be analyzed or described? Which classifications are relevant to our specific goals? Some of the geometry and measurement concepts that are related to the big ideas are transformation, iteration, decomposition and composition, and conservation of space. Transformations refer to the motion of objects and are specifically called translation or slide, rotation or turn, and reflection or flip. Iteration refers to the repetition of units in a way individual units are placed edge to edge without overlapping or leaving uncovered space. The concept of decomposition and composition of objects is similar to that of number. When we have a whole object, we are able to decompose it into smaller objects or shapes, and alternately, we can bring smaller shapes together to create a new larger shape. We understand conservation of space when we can cut a larger shape into smaller shapes, rearrange them, and realize that their area or volume has not changed. In this presentation, these big ideas and concepts will be explored through shapes and tiling.
Shapes and tiles are something that almost all of us are familiar with in our everyday lives. From the pavement to the kitchen, from the checkerboard to the floor, tiles come in a variety of shapes and designs. However, tiling as we understand it informally, as shown with some examples in the pictures above, are not quite the same as what we mean by tessellations. Specifically, regular tessellations as given by their mathematically precise definitions. For example, the three images of tiles on the right of the screen and the bottom one in the middle with the small and the larger squares would not be categorized as regular tessellations, and that is what we will explore and understand next. Here's a shape, here are the four edges. Now when they are being tiled, it has to be edge to edge tiling. If it's not, then it's not called a tessellation. So here, this is an example of a tessellation because you have four shapes which are repeated geometric shapes. You have each of them touching the other edge to edge. And the pattern can be repeated. If we add more tiles, we can repeat this pattern to cover space in such a way that there are no gaps and no overlaps. So I've extended the pattern. There's another important distinction that you find in tessellations, especially regular and semi-regular tessellations, which I will explain in a bit, is that all vertices look similar. What do I mean by that? Here I've circled four vertices. Now, if you look at what's happening at each vertex, or rather each intersection point, you have four right angles meeting to form the big pattern. And if you look here, the same thing's happening. If you look here, the same thing is happening. And that's why this is called a tessellation. There are no gaps, no overlaps, all vertices meet at a point, and there's edge-to-edge tiling. Okay, here's an example of tiling that you would see on the walls or on pavements around us, which would strictly not be called regular tessellations, even though they are all made up of regular polygons, namely squares. The reason being that they are not edge to edge. All the vertices do not meet at a point. And I wanted to emphasize this. If you look at this part, there are two corners meeting at a point, but this one, the edge is at the middle. So one tile meets the other tile only partly at the edge. It's not edge to edge. If I had to make tessellations, I would align them like this so that all the vertices meet at a point and you have edge to edge tiling. Okay, here's another example of regular tessellations using the hexagonal shape. Let's see if this is also edge-to-edge tiling and whether it follows all the conditions that I said are necessary for regular tessellations. Let's look at each of these meeting points. Now, if you look carefully at each of these intersection points, now I have hand cut them, so they are not very precise, and that's why you see those little tiny gaps that are coming in. But otherwise, if they were all perfectly regular, you would not see that little bit of gap. But let's look at each of these vertices. As you can see, there are three hexagons meeting at every point, and if you look carefully, it is edge to edge tiling. Each edge of the hexagon is meeting another hexagon completely at the edges. So that's why this is another example of a regular hexagon. Here's a third example of a regular tessellation using triangles. And if you were doing this in the class with your students, it would be interesting to give your students a variety of regular polygons and ask them to first conjecture which ones do they think would form regular tessellations and why, and which ones would not, and they can actually then play around with the tiles to see which ones tessellate and which ones don't. So we just watched a video introducing some basic concepts and ideas in tessellations. Here's a summary of the key points. This example and this example, in each of these three examples, the tiles that I'm using uh, are a single kind of tile. These three examples, I also mean that they are monohedral. Monohedral means they are tessellations with only one kind of tile, and that's what you're seeing in every case.
During the next few slides, Marina will be explaining semi-regular tessellations. Her explanation will soon turn to exploration, though. You will notice that answering the question, which unit tile is tessellating, will take some time, thought, and exploration.
Okay, so all this time we were talking about the same shape, one kind of shape, or monohedral tiling. For example, all hexagons or all squares or all triangles. Here's a shape in front of us which is composed of two different shapes. You have the hexagon in the middle, and then you have squares meeting edge to edge. And now imagine this being repeated over and over again. Now, I'm sure you can make out we will have all these gaps here. So that's one reason that by itself, this would not make a tessellation. However, is there a way to close these gaps and then repeat that, and would that tessellate? Let's find out. So I'm actually going to just show you this one completed tile. This entire thing would be called a tile, and each of these different shapes. So now how many shapes are there? There's the hexagon, there's the square, and then there's the triangle. So each of these is called a prototile, and all of these is creating a certain shape. Now the possibility is that if I were to repeat this in some manner, I might or I might not get repeated tessellations. We'll see that in a minute where I show this to you with images to check every intersection point. So here you have a hexagon, two squares, and a triangle. If you look at another point, the same thing is happening there. So here's the pattern. Now I've extended it. So there's the hexagon, there are the squares. Ignore the different colors, but they're all still the same size squares. And you have the triangles. The point we're trying to see is whether this is tessellating by making sure that it all follows, the same rule for the vertices. So let's start here. You have the hexagon, square, triangle, square, in that order. Let's look at this one. Hexagon, square, triangle, square. Let's look at this one. Hexagon, square, triangle, square. So wherever you put this, it's going to follow that rule. The reason it's called a semi-regular tessellation is because it's using more than one kind of polygon. So two or more types of regular polygons arranged in a repetitive pattern so that every vertex point is identical is called a semi-regular tessellation. To sum up, semi-regular tessellations include two or more types of polygons arranged in a way that each vertex point is identical to the other. And these are marked by the red circles in the figure on the right. I also want to point out to you the two squares, the triangle and the hexagon. the entire set is outlined in red lines, it would be a mistake to imagine that that would be the set of shapes that are getting repeated. If you actually took a tracing of that and laid it next to each other, you would find that it would not tessellate. And I had a very interesting exploration when I tried to find out what was the set of shapes that actually tessellated to create this pattern. Here are some of my experiments. I first tried to tessellate with the red outlined set of shapes that was given in the previous slide. The result is shown on the left. Rotating and trying to fit them in different ways still left gaps. That is when I searched on the internet and found the set of shapes given on the right. You can see my attempts to tessellate using this new set, and you can see the gap marked by the red circle. The gap could be filled by a square and a triangle. So next I added these to the image I found on the internet. And this is the result. We hope that by sharing this trial and error process here, you can see how students can be encouraged to do the same with shape styles in the classroom, which in turn will help them with spatial and geometric reasoning. We have discussed regular and semi-regular tessellations extensively so far. We now come to non-regular tessellations. A non-regular tessellation is a tessellation that is composed of shapes that may or may not be polygons, and if they are polygons, they need not be regular polygons. There is also no restriction related to the order of angles around a vertex. These examples of non-regular tessellations are from student work, where they started with a basic square tile and then modified that tile using their own creative ideas. Students really enjoy creating their own tiles. My colleague Anani Vasquez will now guide you through creating your own non-regular tessellations.
In this video, we will walk through an example lesson. First, it's important to note that your students should have already had many and varied experiences with tiling, especially with regular and semi-regular tessellations. For this activity, you will need 10 to 12 squares. These can be made from a 10-frame template or graph paper, or they can be cut from construction paper. In order to prepare for this lesson for the classroom, each student will need 10 to 12 squares, a ruler, scissors, and Scotch tape. Consider accommodations such as left-hand scissors, adaptive scissors, and maybe even larger graph paper, inch-size graph paper. Today's task is to determine if we can make non-regular shapes that tessellate. You'll need to begin with one square and your scissors. You're going to make one cut along one edge of the square so that you have two pieces. This cut can have curves, it can have straight edges. It's up to you. So I began with my square. I made a cut along one edge. The next thing I'm going to do is slide one of the pieces to the opposite edge. Now I've created a non-regular shape. In order to make more of these shapes, I'm going to trace my cut it out, slide, and use Scotch tape to tape my pieces together. So I should have 10 to 12 non-regular shapes that all are exactly the same. Here are a couple other examples. This was my first attempt. and that's my cut. I can slide it over to the other edge, opposite edge, to create my non-regular shape. And this is my final non-regular shape. Another example is here. This was my cut. I slid this piece over to the opposite edge and created a new non-regular shape, and that is how it ended up. Now, if you want to try something a little more advanced, once you've done this and created a non-regular shape, you can then take one of the other edges, say the bottom edge, cut across, take that piece and slide it up to the opposite edge. Here's an example of one that I attempted. This was my second cut, which I can then slide across and tape to have another kind of non-regular shape, one created with two cuts. So take a few minutes right now and create for yourself a non-regular shape. Now that you're ready with your non-regular shapes, various copies of your non-regular shape, you are ready to begin exploring. This is the question we are going to ask ourselves. Does our non-regular shape tessellate? So we're going to take a few minutes now to determine whether we can tile with our shapes in a way that edges line up to edges, there's no overlapping, and there's no extra spaces in between. So take a few minutes and play with your non-regular shapes. Do they tessellate? So while you were tiling, what did you notice? What did you try? What else do you think you could have tried if you had more time? How did your shapes fit together? Did they repeat like mine do? Did they rotate? Did they flip or reflect? These are some of the questions you can ask your students as they are exploring, as you walk around the room monitoring. Once you bring the class back together, have your students share some thoughts. If we were working right now synchronously, we would take some time to share our thoughts, share our noticings, share some of the things that we found out while we were exploring with our non-regular shapes. So once you bring the whole class back together, you might want to ask, do all non-regular shapes tessellate? When might a non-regular shape not tessellate? You might go back to the question about what kind of transformations do you notice in the designs that you created with your tessellations. Depending on your objectives and on the noticings of your students, the whole group discussion could lead in a variety of directions. For example, you might try designing a non-regular shape where the cut piece is rotated to an adjoining edge, like this. Instead of sliding, what would happen if you rotated in this direction or rotated in this direction? Would this non-regular shape tessellate?
You might explore how perimeter and area change or stay the same when a square is cut and reconfigured. For this example, you want to make sure that the measurement of the edges of the square are appropriate for the students that you're working with. For example, these squares are 1.5 inches per side or per edge, making a perimeter of 6 inches. And these squares on the graph paper I have created are 10 centimeters per side, making 40 centimeters as the perimeter to be 40 centimeters. The graph paper, though, is a good choice for students who are just beginning to have a good understanding of area. The design tessellations that you've created can also be displayed as artwork. So there are so many different directions you can go into, and definitely continue discussing those transformations, the sliding, the rotating, the reflecting. Depending on your age level, you might decide which terms you use for those transformations.
These are two different examples of non-regular tessellations. The first by Jill Etheridge and the second by M.C. Escher. Marina and I have attempted to share big ideas, concepts, and instructional strategies that can be used in the classroom. Although we have walked through some examples, we have not modeled exactly how we would teach to our young students using rich tasks. The last part of this presentation will explain the importance of teaching all students using rich tasks. Rich mathematical tasks must be accessible to everyone from the very beginning, as well as extendable. Rich tasks should involve children in speculating, hypothesis making and testing, proving, explaining, or justifying, reflecting, and interpreting. Rich tasks should not restrict children from searching into new directions. They should encourage originality and invention and what if or what if not questions. Rich tasks should also be enjoyable. Rich tasks, as we have described here, are inherently dedicated to creativity and divergence of thought. As educators, though, we can intentionally design our lessons for creativity, diversity, including cultural diversity and neurodiversity, and equity. Next, Marina will talk about creativity as it relates to rich tasks, including tasks about tessellations.
So we really hope that the above examples of student work, as well as our instructional videos, show you that tessellations spark creativity in the math classroom. And this is true not only for students, but for teachers as well. When talking about creativity in the classroom, Begetto, a creativity researcher, identifies 3 kinds of creativity. Very briefly, the first one refers to understanding creativity as a topic. For example, when you're discussing different definitions of creativity. For our purposes, the second and the third are more important. The second one uses novel or innovative pedagogical tools and strategies, and the third relates to teaching in a manner that encourages creativity in students. Including the topic of tessellations in the geometry classroom can help you teach with creativity as well as teach for creativity, developing creativity in your students.
Rich tasks should be designed with creativity and for creativity. Next, Marina will give examples of how to incorporate cultural and historical aspects when teaching with rich tasks, specifically tessellations.
Tessellations have been found in different cultures over different time periods in history. For example, the topmost image is of the decorated pillars that was located in ancient Mesopotamia, which is modern-day Iraq. These pillars date back 5,000 years. The lattice windows on the bottom right are from China. These were used in ancient times and continues to be used today. The colorful image in the middle photo that's at the bottom of the slide is a photograph of tessellations from Alhambra in Spain, which is a World Heritage Site and one of the finest examples of Islamic architecture. Islam forbids the use of images of humans or animals, and thus Islamic architects and artists developed a wide variety of intricate tiles and tessellations to decorate their creations. In fact, these patterns influenced Escher to create his own tiles, which is something that Anani, my colleague, showed you earlier. These images shown here would work well as the launching point for a unit on tessellations. The students in our classrooms are increasingly diverse, coming from different religious, ethnic, and cultural backgrounds. Showing examples of tessellations from different cultures would enable the students to look beyond Eurocentric framings of mathematics and thus help rehumanize mathematics for the students, as Gutierrez would talk about it. The above images are also evidence that sophisticated geometric thinking existed in ancient times as well as in cultures around the world.
We will show you one more tessellation, an irregular tessellation today that starts off with a basic regular polygon of the triangle, and then we cut shapes out from one side, stick it to the other side. So you can see this was the original triangle. This piece was cut and kept here. This went from here and this came from here. So from the triangle, I got this shape, and then I have 3 more of these. So now I no longer have a polygon, but let's see if this shape tessellates. As you can see, it does tessellate. Imagine having 3 more pieces like this. It'll form a design, and let's take that edge, move this around and see if that fits in there. It does. So which means this pattern can be repeated indefinitely. So this was in fact the Alhambra tile that I showed you in the slide before this. That's how this shape was made.
Valuing and encouraging diversity in the classroom leads to inclusive math learning environments. Hodges and colleagues stated, children from different backgrounds are likely to bring cultural ways of participation that may be different from the ones expected by the school. I think it is worth noting that students who belong to non-dominant groups often have rich experiences and skills, such as knowing more than one language, important in a global world, knowing how to collaborate, important for teamwork, a trait that is valued in many professions, learning at home through participation in the activity rather than through direct teaching, contributing to the household functioning, For example, helping out with the home economy language brokers. Hodges and colleagues continue by stating or by questioning, what are the implications of this richness of skills, knowledge, and experience for teachers and researchers in mathematics education? In valuing cultural diversity, we are valuing experiences and modes of knowledge that go beyond those of the dominant culture. In the same way, we can value neurodiversity as multiple forms of being and knowing that are personally meaningful to individuals whose life living experiences extend beyond neurotypicality, or the dominant modes of thinking, learning, communicating, and interacting. Neurodiversity engenders new ways of communicating about difference by celebrating neurological and behavioral diversity across humankind, emphasizing that there is no one normal or ideal way to be human. Lambert stated, when educators assume that students with learning disabilities are not capable of developing strategies or of learning from inquiry-based methods, these students will be denied access to a well-rounded, rigorous mathematical curriculum. She goes on to say, students with learning disabilities, as well as those who are labeled as low achieving in mathematics, are offered a more procedural mathematics when compared to their peers. The documented positive outcomes of an inquiry approach to mathematics, not only in mathematical knowledge, but in developing student identities as agentic problem solvers and a positive relationship towards mathematics, mean that we can no longer allow such beliefs to curtail the mathematical potential of students with learning disabilities. Neurodiversity is valued in schools when strengths and challenges are assessed instead of deficits and disorders detected. Strengths are built upon instead of weaknesses remediated. And human potential is developed instead of standardized skills and objectives being covered. Neurodiversity is valued through rich tasks when they are accessible to everyone and encourage divergent thought and divergent thought processes. When we design rich tasks in ways that teach for and with creativity and that value cultural and neurodiversity, we are developing equitable learning experiences and environments for all students. NCTM considers beliefs and expectations, curriculum and instruction, interventions and supports when they are evaluating for equity. We know from research that tracking is not equitable and that meaningful engagement in math is necessary for all students. Using rich tasks and enjoyable topics such as tessellations, we can increase equity across our math classrooms. We begin with a strong commitment to teach all students in our classroom settings. We ensure that all students are given supports when needed. We ensure that all students are challenged to think critically and creatively. And we believe that all students have important ideas that others can learn from. We have enjoyed working together to prepare this presentation for you, and we look forward to further discussion during the virtual conference. On this slide, you will find example standards for the lessons discussed in the presentation. On the next slide, you will find references for the scholars cited. We hope you are able to take the rest of the time from this session to go back and enjoy Tesselations. Spend some time exploring and creating on your own. Thank you for joining us.